All right. Today we're going to dig in on some seemingly well-understood concepts as they relate to databases and to DynamoDB in particular. The statements you see here may include some common fallacies and misconceptions. Through this session and the next, we'll present information that will help you to make your own evaluation of what is possible with DynamoDB. AWS offers a growing range of database options, effectively a spectrum of capabilities and strengths for indexed data storage. So where does DynamoDB fit in? Why would we choose DynamoDB? And do those reasons provide some guidelines for us as we design our data model?
Hey everyone, my name is Rob McCauley. I've been here at Amazon for 7 years. I started off as a database developer at Amazon Robotics. I spent some time at Amazon Alexa as a solutions architect, and now I'm a specialist solutions architect with AWS, focusing on NoSQL and DynamoDB.
All right, and I am Pete Naylor. I'm another one of the specialist solution architects for DynamoDB on Rob's team. I've been with AWS almost 4 years now. The first 2 years I was on the account team that supports Amazon.com as a customer of AWS. And my primary focus over those 2 years was supporting them through some fairly ambitious database migration goals. Many of those migrations were to DynamoDB. I learned a lot about the service along the way and really became a big fan. So more recently, in my current role, I've been working more with external customers, and I'm really having a blast. So glad to be here today to discuss this stuff with you. Welcome to this second series of virtual sessions about DynamoDB. The season will have 2 episodes. The first episode will discuss some of the techniques employed to support more advanced designs, those that extend well beyond the simplest of have key, get value. In the second episode, our friends Sean and Rick will build on these techniques and demonstrate use of the new NoSQL Workbench as a tool for designing, visualizing, documenting, and developing operations with DynamoDB as an indexed data store for an application or a service. I want to point out that we're going to move fairly quickly today. We have a lot of content to get through. We do have a lot of folks from AWS online to help out. I see we also have Alex Debris online. He's going to help out answering some of the questions. Thanks for joining, Alex. Alex just wrote a really pretty amazing book about DynamoDB that I highly recommend. All right. So why DynamoDB? Let's start by building an understanding of why we built DynamoDB. Understanding its strengths will help us to use it well.
Yeah, here we see a screenshot of our manager, Siva Raghupathy, as he was delivering a session called Big Data Architectural Patterns and Best Practices at reInvent 2017. What I like about Siva's diagram here is that it shows the various storage options as a spectrum. There are certain inescapable realities about data storage and indexing, and you might have heard of the CAP theorem, which expresses some of these trade-offs that we have to make. Different technology options make different choices based on priorities. There is no one technology that can optimally deliver everything at all extents of the spectrum. And this really explains the AWS database strategy. We want to provide options that cover this spectrum. We want to offer a continuum of technologies so you can choose the right tool for the job. In fact, we often see multiple technology choices combined for the same data set to really optimize a customer experience. Consider the polyglot persistence concept. So DynamoDB doesn't replace traditional relational databases, but rather you can think of it as a complement. It's a purpose-built database for a particular set of priorities.
Right. So where does DynamoDB fit in that range of data stores, and what are the associated priorities? Well, DynamoDB is an operational database. This means we want those ACID properties. We want atomicity. We want consistency. We want isolation and durability. We want to be able to create, read, update, and delete records, and to have some conditional controls around those mutations. We need to be able to index these records for easy retrieval, including some sorting and some filtering functionality. These are all things that fit an operational or transactional type of requirement. This is live data. But AWS wanted to further refine DynamoDB to place greater focus on availability and performance. We want to offer something that fits well for our most critical of use cases, the kinds of places where downtime, either planned or unplanned, is simply unacceptable. It's going to result in a poor customer experience. Scalability and management complexity are very real risks to those requirements. Amazon.com learned this over 15 years ago, and that prompted a new approach, ultimately leading to AWS providing the DynamoDB service. We made some assumptions along the way. First, that conserving storage space slips to a lower priority. We're willing to store more in order to get the consistent performance and the scalability that we desire. Storage is relatively much cheaper than compute, than we might have seen 30 years ago. Second, we need to be able to scale horizontally through sharding. And we wanted a distributed database, but the sharding and the infrastructure management had to be fully automated. Third, dependency on centralized compute for answering questions about our data is not acceptable due to the scaling ceilings and variability in latency. So the idea is to pre-build all of the answers that we can and store them so that they are ready for efficient retrieval. We solved the automated sharding using a hashed value to distribute the data across logical sections called partitions. And we handle all of that within the service, including the scaling. We let go of constraints around the attributes in each record, allowing for a flexible schema. And finally, we recognize that eventually consistent read after write is acceptable for many activities and sometimes advantageous. So we give the option of strong or eventual consistency each time a request is made. By the way, is anyone seeing anything missing on the list from the slide? See anything there, Rob?
Well, what about security, Pete?
Yeah, so security, of course, it's the highest priority, and that's true for all AWS services. And you can assume that security is right up there at the top of the list.
Of course.
Oops. All right, so we want to basically go over some of the basics for DynamoDB up front. I know this is an advanced session, but I want to make sure that everybody is up to speed before we really get into some of the deeper discussion.
Great. So there's a concept out there called normalization. And in the early days of relational databases, this represented an approach to modeling your data with two main objectives. First is to reduce data duplication, and the second is to try to maintain the integrity of views to your data. Due to the high cost of durable storage at the time, reducing the overall data volume was a high priority. If we look at the example shown here, you can imagine it might be a retail sales application. There's a table which stores orders, another that stores information about customers, and a third stores merchandise details. Looking at the orders detail table, we can see that customer 100 made 2 orders, but we don't record cust 100's details twice. We can reference that information from the cust 100 record in the customers table. Same is true for product 300. It was part of 2 different orders, but we only record the product details once, referenced by product 300 in the products table. So you can see how this reduces data duplication, but it comes at the cost of something called a join. A SQL database with normalized data structure depends on CPU to go get the various entities from the tables to build a complete result for the application. As time passed, storage became much cheaper relative to CPU, and latency expectations tightened. Latency results for a request that relies on a join can vary with the level of CPU load. And the cost of storage relative to compute was dropping. Many Amazonians were deciding that normalization for the goal of data reduction was not really a winning plan. So they started to denormalize. They were recording complete results in a single row so that a join was not even required. The join was essentially done prior to writing denormalized items. Cool, so I guess we should just denormalize everything, Pete?
Well, wrong. The second objective for normalization is still valid even when scalability and low latency take priority over storage efficiency. Let's take another look at our orders table and think about our business process. Customer 100 placed an order for 3 product 300s on June 12th, and customer 102 placed an order for 2 of the same type of product on June 15. So how does this look if the price of product 300 changed from $42.95 to $39.95 on June 14? Well, if we go to look up Cust 100's order information from June 12, it's going to reflect the new price. is that really what we intended from a business process perspective? This might produce anomalous behaviors, which are not cool. If we wanted to keep an immutable history of orders as they were placed, including the product price at the time of that order, we might denormalize that information and record all the details together in a single row. But if this is a live shopping cart, we might actually want to normalize, keeping the cart as a set of items and fetching the most up-to-date pricing for each of the items only when we're required to for checkout. If we stored the items' prices in the cart, we'd need some kind of asynchronous process to find and update all the relevant carts when an item price is updated. And maybe that's okay in some cases. You know, maybe the price changes and we want to kind of asynchronously go and find out who has that item in the cart and just let them know that the price has dropped. But it's not necessarily the right approach for every use case. And we can note that the same consideration also applies to DynamoDB. Normalization is a choice. Sometimes we'll record the details together, and other times we want them to be separate. And we'll look them up as required by reference. This is often accomplished using a join in a relational database. We can do something like this join in our DynamoDB client too, by looking up multiple distinct records in parallel, if possible, and piecing them together to achieve our objective. There will be a compute component to this activity, but it's going to happen on the client, and we can scale the client side horizontally.
All right. So from a relational context, we might historically have normalized to save storage where possible, but we should all agree right now that when we want to optimize for consistent performance at any scale, we have to forget about normalizing to reduce storage requirements. Make this choice purely based on the way you want your data presentations and questions to be answered, and avoid anomalies. A couple of last points before we move on from this topic. Note that for a relational database, each table has a fixed and enforced schema. So when you're storing referentially related information in separate records, they are stored in separate tables. Different entity types have different columns and attributes, likely for different data types also. And if you look at the column for product color in this products example here, you'll see that if color doesn't apply, we still have to store a null. DynamoDB, of course, has a flexible schema, so if an attribute doesn't apply to the item, we can just leave it out. This schema flexibility also means we may choose to store multiple entity types in the same table. More on that later.
All right, so let's start out covering some terminology. How do we refer to different parts of DynamoDB? The first layer of abstraction, I guess, or the first concept is the DynamoDB table. This is just the collection of items that we want to store together. We're going to store items in the table. These are a lot like rows in a relational database. In this case, for our example diagram here, we have 3 different items. Each of those items is going to have a set of attributes associated with them. And you can see here that the attributes don't have to be the same. It doesn't have to have the same schema in every item.
Interesting. So no more, instead of rows and columns, it would be items and attributes, right?
Yeah, exactly. Very similar concepts. We also have one of those attributes that is required for every item in the table. And that attribute is our partition key. That's what DynamoDB uses to do the horizontal scaling. We're going to hash that effectively and figure out where on all of the infrastructure we're running for you, where it belongs. You can also add an optional sort key, and this is used again to help uniquely identify the item in your table, but it's not used to broadly distribute your items. This actually, using a sort key, allows you to keep those items together. You're going to say, these items are related, I want to keep them together, and maybe I want to be able to pull a range of those more efficiently. Together, they're going to form a primary key. So the primary key will include a partition key and an optional sort key. This becomes a unique item identifier in this table, which is really our primary index. So again, just to dig a little deeper, the partition key is what we use when we want to model a one-to-one relationship in DynamoDB. It helps us to distribute the traffic, and we want to have hopefully a nice even distribution. It also helps us to identify which collection we're interested in. And when I say collection, I'm really referring to the collection of items that are defined by a sort key if we have one for our table. The sort key allows us to manage one-to-many relationships. It collects these related items, and it provides for efficient filtering and sorting. So what do we mean by that, that efficient sorting and filtering, Rob?
Well, yes, we can do query operations against the table specifying a partition key for our collection. And then within that, we can do these range operators that you see here. We can do certainly inequality. We can do greater than, less than, begins with, and between. And this lets us sort of navigate through this B-tree index of the sort key, find begin and end ranges, and then scan through the results and get results sorted either forward or backwards alphabetically.
That's cool. So each time we make a choice, we can specify whether we want forward or reverse sorting, and we can even set a limit on the number of results we want back. So we could actually say, give me the first 3 or the last 10, right?
Mm-hmm.
It's really pretty cool. All right. How about secondary indexes?
Yeah, the idea of secondary indexes, let's start with global secondary indexes. This is what you'll probably see and use most often. And essentially, it's like a relational database index. It's a second view of data, if you will, like a materialized view. It's maintained by the table itself. In this case of GSIs, or global secondary index, we regroup the data according to some other attribute. So while the base table is partitioned by attribute A1, maybe this other GSI is partitioned or collected item collections based on A2 or A5 or A4. You can choose. And if it finds a data in that attribute, it'll add it to the collection and regroup for you. And this makes a very powerful view into your data. Right? Different users of your application might have totally different views, requirements. The GSIs can include the keys only. They'll always include the primary key of the base table. They can include all of the attributes in addition to the base table, or they might include some. So you can selectively project different attributes into the GSI, just like you would a materialized view in a traditional database. Right? You can also think of, I've heard them called an inverted index. Right? The other type of secondary index we have is a local secondary index, or LSI. And these are not quite as flexible as a GSI, but essentially it's using the same item collection, the same partition key, but an alternate sort key. So you're able to maybe sort by something else and do different range queries against the LSI's sort key. Some limitations, though. You have to create the sort key when you create the table. You can't add it after the fact. And if you do decide to use LSIs, then the whole size of any one item collection has to be under 10 gigabytes at all times. So they can be useful, but just keep those in mind.
Great. All right, so let's dig in on the basic low-level API for DynamoDB, because we don't talk to DynamoDB using SQL. We offer a range of different SDKs to make working with DynamoDB easier in different programming languages. But underneath those SDKs are a fundamental set of APIs, low-level APIs, that it's great to understand because it helps us understand how to model efficiently and effectively. The first thing we should say is that DynamoDB, the way that we look at your consumption or how your bill will be calculated, is based on the overall size of your data set, and that can grow and shrink. You're really only billed based on what you're using at any particular time. And then there's this concept of write units and read units. Let's talk about the write operations first. A write unit is essentially a write of anything up to 1 kilobyte per second, and those are rounded up. So if you could imagine, we might want to make a write which is 2.5 kilobytes in size. We're going to round that up and say that's 3 write units. An important thing to understand is that when we're making a change to an item, the way that DynamoDB is going to figure out how much write consumption to assess is it's going to look at the larger of the new and the old image. So if we look through these operations, the put item is how we're going to be able to provide a complete view of what our item needs to look at, and we're just going to hand it to DynamoDB and say, write this into the database. If we don't provide any kind of conditions on that write, which we can do a lot of powerful conditions saying maybe don't overwrite this item if it already exists, if this primary key already exists, or any other set of conditions that we could place on that. If we don't, it's going to be an upsert. It's just going to replace whatever the item is that's there. And so the larger of the two images is what the write consumption will be based on. Update item allows us to update just selective parts of the item, particular attributes that we want to give a new value to. We don't have to know what the rest of the item looks like. DynamoDB will fill that in for us. But the important thing to note here about update item is that when we make that update, we're essentially going to ask DynamoDB to rewrite the whole item. And so again, we're going to look at the size of the item. We could make an update to one small attribute in a 8 kilobyte item, and that's still going to be assessed as 8 write units. In the case of a delete, again, we look at the larger of the new and the old image. So the new image is 0, right, because the item's gone, but the old image may have been a 15 kilobyte item. So the cost of making that delete is 15 write units. We have a batch write item API, which allows us the convenience of bundling a number of put item and delete item requests in a single API call. So it avoids some of the network back and forth. This is a great operation for bulk updates. But batch write item is going to essentially be on the DynamoDB side, just like breaking out those individual put items and delete items, and you'll be assessed the write consumption just as if you'd done them separately. One thing to note that is important, and we'll see this a little bit further on, is that our GSIs and our LSIs, they consume write consumption also. When we make a change in our base table, which gets propagated into those secondary indexes, whatever is propagated, whatever we decide the attributes are we want to selectively project, whatever the size is of the indexed view of the item, that will be assessed as a write consumption also. So something to keep in mind here in terms of efficiency. So let's move on. Rob, you want to cover some of the read throughput?
Yeah, for sure. Read, there is no SQL select, right? There are these simple API calls that you can make to Dynamo to get data out. Get, scan, and query with a batch get flavor of get. Get's the simplest one. Let's start with that. This is the idea of a key value lookup. You provide a key, and we'll find the record for you and return the complete record. For all these writes, the consumption that you'll be charged for is against these read units, or RCUs, they're sometimes called, and they're 4 kilobyte units. So if you got an item that was 3 kilobytes, we'd round up to 4, and that's what the charge would be. Get item is by default eventually consistent, and that gives you a 50% discount on the nominal cost of doing a read, or RCU. If you wanted to do a bunch of reads together, you can do what's called a batch get item, and effectively, for convenience, you can pass us up to 25 keys that you'd like items for, and we'll return those records to you if they exist. We also have scan. Scan is a very simple way to take a look at your entire table and just return all the records from top down in no particular order. You'll get paginated if you have a large table with more than a megabyte. You'll get 1 megabyte at a time, and you'll have to rescan with a bookmark to get that whole table out. And then I think all of our favorites is this query operator. This is a cross between get and scan, right? So now we can provide a partition key and get back an item collection, a complete collection, or perhaps do those range operators against the sort key further. We'll see some of that in our demos.
Awesome. And yeah, I mean, one thing to really recognize is the only one of these that you don't have to provide a partition key value for is that scan. So, okay. I really want to highlight this powerful functionality in DynamoDB called item collections. Remember that we mentioned a table with composite primary key, and it allows us to collect these items together. They're related basically by that partition key value, and that defines our item collection. It allows us to narrow our queries by saying, look in the item collection identified by this particular value of partition key, and fetch me a filtered and sorted set of the items based on the parameters that I provide. So this is very cool, right? It's really quite powerful. It's very easy to imagine a model that would use something like maybe an IoT device ID as the partition key, and the timestamp of a periodic sensor reading as the sort key. The reading itself, the measurement, might be recorded as an additional attribute. But now in this model, we can do these time-sorted range queries for a given device. And that's not all. Remember we said that query aggregates the item sizes for these read unit consumptions. We can potentially retrieve many matching items from a collection in that range query, and it might just cost us that basic 0.5 of a read unit with eventual consistency. Item collections are an amazing tool. Now, the sort ordering is not always important. What's most important is that an item collection allows you to logically group a set of items. They're related by that partition key value. All right, so now let's recall that DynamoDB has schema flexibility. This means that the items with different sets of attributes, different schema, can coexist in the same table. These are potentially very different entity types. In fact, they can also be related by an item collection. And that item collection can be in the base table, the primary index, or as we'll see soon, in a secondary index, a global secondary index. Okay, so now let's hold on to your relational database hats, because what I'm going to suggest is that when you query a DynamoDB item collection containing multiple types of entities, it's kind of a lot like a join, right, Rob? It relates records of multiple entity types, and you can get some very neat sorting and filtering capabilities as a bonus. This join is powered by a highly scalable storage platform, and the performance is very predictable. So let's keep this thought in mind because it's foundational to the rest of this series. Also realize that to take advantage of this awesomeness, the items that you want to collect, be that in the primary index in the base table or in a secondary index, must exist in the same table. Note that the item collection is still materialized. We're still storing our data with the aim of being able to build our answers quickly and efficiently.
Yeah, I was going to say, I love this item collection concept. I think we should use this. The word partition, I hear it used all the time. It gets overloaded, right? People sometimes think of the partition as the split between sets of data, or even as a verb, something that happens, right? Or they partition meaning a group of data. But if we think of item collection as a logical set of data, it'll help to clarify what we're talking about.
Yeah. For us in DynamoDB, a partition is really kind of a logical segment of the storage. It's how we're going to do that horizontal scaling. It's not really the same thing as an item collection at all. So let's move on. Concurrency control, also important.
Yeah, here's an example of a concurrency control. We see this all the time as multiple users are accessing the same table and potentially stepping on each other's toes. In a traditional database, you might implement full-blown transactions, which are hard, can cause a lot of pain if the transaction stays open and locks happen and locks escalate. So we don't have locks within DynamoDB, but we can do something clever, I think, with just this optimistic locking algorithm. And the way it works is like this. Let's say we have a shopping cart that multiple users are working on. We can take a copy of that cart, go and maybe make some changes to it, come back a few minutes later and try to rewrite that cart. We'll say, hey, write this cart if and only if this version attribute that's in there has not changed, has not advanced to some future version. If it looks the same as that when I read it initially, then I know it's the same, and I can go ahead and apply my changes and not overwrite anyone else's. And then I'll increment the version as well to notify anyone else watching that their version might now be out of date. So this optimistic locking is a great way to handle lots of users before getting into full-blown transactions, which we do support. More on that later.
Yeah, great. So let's talk about idempotency and atomic multi-item transactions or operations. These are really exciting to me. It's a relatively newer part of the DynamoDB service in the overall picture of our history. By the way, DynamoDB released in 2012 and still adding these new features that are just mind-blowing to me, to be honest. They open up so many new use cases. So the two APIs that we added to support these transactional workflows are transact get items and transact write items. Transact get items is really just there to give you kind of an ability to read a number of different items, up to 25 of them, and know that all of those items existed in that state together at the same time, exclusive of any other operations or transactions that may have been going on. So that has its own use cases. But to me, the really great API that we offer is transact write items. And this allows us to update, put, delete, or check across 25 different items, 25 different operations in that transaction. And it's all atomic. It's all succeed or all fail. So this can actually be done across tables. As long as the tables are in the same AWS account and region, we can use those items. And it's capable of doing complex conditional checks. So we can place conditions on the individual updates, puts, and deletes, just as we could if we were doing them individually. And we can also use this check operation, which is to say that, I want to go and take a look at this other item and make sure that it has this particular value. And without that value being true, I want you to fail the overall transaction. But we're not actually modifying that particular item. So some of the good use cases here, is maybe to commit changes across items. If you had an example, probably the classic example, right? An online bank, 2 different accounts, 2 different customers, and they want to do a balance transfer. We want to be able to, as an application developer, we want to be able to promise that user that we can take money from one account and put it in another account, and something's not going to go wrong in between. We're not going to be left in this situation where things are hanging and the money is kind of missing, actually. Using transactions allows us to do that as an all succeed or all fail operation, and it's something that you make the request and get the result. There's no open a transaction, do a whole bunch of things, and then maybe forget about it and go off and do something else and then come back and commit it. This is an operational one-time thing with DynamoDB. You get the response right away saying whether it worked or it didn't. It's also great for conditional batch inserts or updates. Maybe we talked about these item collections. Maybe we want to make sure that we're adding 4 items at the same time and make sure they all succeed. Or maybe we want to delete all of the items in an item collection if it's a small collection. We can wrap that in a transaction. So a lot of really powerful use cases there, I think, I really think we're just starting to see the beginnings of some of the powerful things that customers are going to be doing with these. The flip side to that is maybe the bad use case, right? What we kind of want to discourage. And that is, if you were to bring your traditional relational mindset and start building a table in DynamoDB for each entity type, and now you kind of have to use these transactions to manage things together at the same time. You may have missed an opportunity there to denormalize. Keep all of that information together in one record, and now that it's one record, we don't need a transaction. Actually, we can just use that optimistic locking pattern, and we have atomicity because it's a single item. So just something to keep in mind when we talk about transactions.
Awesome. All right, so a quick look at some data types, the core primitive data types of DynamoDB. The ones you'll see most often by far are the string and numbers, S and N. And these correspond to strings or varchars in your app or numbers, either integers or floats. And then timestamp is really whatever you want it to be. It's something you send in either as a number, perhaps as a Unix epoch time, number of seconds, or as a string in your favorite string encoding like ISO 8601. And then they'll be just stored as a string or number. We also support blob for binary objects, which might get some storage space as it's compressed with base 64. Some more powerful ones that are composite types are there. There's array and a JSON document, a map. I'm a JavaScript guy, so I think of that as arrays and objects, or part of JSON itself. So you can nest these together. You can have lists of maps of lists, or maps of lists of maps. So you can really implement a full-blown document as your application needs to, and store that within these objects. You also have a set operator. It's less common, but this is essentially like a list, and it enforces the fact that every item in the list, in the set, has to be of the exact same type.
All right, so let's talk a little bit more about those strings and numbers and how it matters when we make that choice. And we'll put this in context of a date storage. In DynamoDB, there's plenty of times that we want to store a date, and we have different ways that we could choose to do that. We could represent the date or a timestamp as a string or as a number. Very commonly, we would use an ISO 8601 string format that allows us to do that nice sorting that we want to be able to do over timestamps. Pretty great, right? And it's very, very readable. It's nice to work with. That will actually store, that string will consume 20 bytes in a DynamoDB table. And that doesn't sound like much, but some of these use cases that we're seeing customers with have billions and billions of items in a single table. So if you can imagine, this will add up, and perhaps we might have chosen instead to store it as an epoch timestamp or an epoch date, which will be this number format that we see, and we could store that number either as a string or a number. When we make that choice, though, if we store it as a string, it's going to consume 10 bytes, which sounds pretty good compared to 20, right? But the number format will allow us to store that same information in only 6 bytes. And this may feel a little bit nitpicky, but as I mentioned, we have customers that are running use cases on DynamoDB that are extremely large scale, and the storage around these items does add up, and so the choice of number or string is important. One thing I would also add is that in this particular scenario, we have a feature called TTL, which allows you to set a timestamp after which DynamoDB can delete the record for you. It will expire it, and that delete will be free of charge, which is a super great tool, right? It's an amazing tool. What you do, though, is you're going to set that timestamp for expiry using an epoch timestamp, and it must be stored as a number. So be aware of that. One thing I should add also is, on the topic of how many bytes are consumed and everything, this affects not only the overall storage, but if you think about that aggregating ability of query, where we can get back many records for a small amount of RCU, we could get thousands back, and the number of bytes in each record is going to add up. It is important. To that topic, when we store an item in DynamoDB, we're going to store, because of this flexible schema, we're going to store the attribute names. So if we're storing a really long attribute name, very descriptive, maybe 50 or 60 characters, we're going to store that for every record. Thinking about that and keeping those attribute names short is kind of a nice little trick for optimal efficiency with DynamoDB.
Mm-hmm.
All right, we should talk about, now we've covered a lot of the basics, I think. I feel like that was a lot of what we need to build on. So how do we put all these indexes to work, Rob? What are we gonna do to build some more advanced use cases?
Oh, great question. Yeah, for sure. So as we start to think about how our data might be accessed, we have to keep in mind there's two main ways that we might essentially limit or select certain items out of the table, right? And these are sort key conditions and filter expressions. They can often work in the same way. When I first learned Dynamo, I really thought queries and scans were the same. I thought sort key and filter were the same, but they're very, very different, as we'll see. The sort key condition is perhaps the most powerful. This is the ability to use the sort key itself in order to limit the items, to do a query against a partition key, giving item collection, and then something that looks at the sort key, either equal or greater than a value or between two values, something like that. If that's not available, if you really need to get items out, like with the status here, against the base table, if it's not part of the sort key, then we're default with getting all the items and sorting ourselves in the client app, or doing what was called a filter expression. So we can ask DynamoDB to return these items, but knock out the ones that we're not interested in. So we'll still be charged for the cost of reading the original items before the sort happened, before the filter happened. But at least we won't receive that many items coming back at us.
Right. So yeah, in this case, there's 3 different items for a cart here for our customer ID Sue, and we can get back just the active items and filter out that saved item. In this case, that's pretty efficient, right? It's not really a bad filter. But if we looked at this and thought, well, Sue might have thousands of saved items, now we're literally going to be throwing away probably the bulk of our saved our entries that we're going to have DynamoDB consume read capacity on.
Mm-hmm.
So I think, Rob, you have some demos here, right, that we can walk through just to really bring home some of these efficiency concerns and the way that the different APIs are assessed in terms of their consumption.
Yeah, absolutely, Pete. Yep, you'll see in the link bit.ly/DDB efficiency. You can try these out tonight if you like. But what we've done is set up a table called shopping cart. We love shopping carts here. The base table here has a composite key. The partition key is like products, customers, but mostly cart items, individual carts. And within each cart, we might have different products that have been added to that. And then a whole bunch of attributes. And many of these attributes are quite large. They're 20 kilobytes. So we'll see how that comes into play. We're also going to do something. We're going to run a bunch of Unix shell scripts that are going to return consumed capacity. So let's take a look at the first one here. Let's do a scan script. So it's going to do the command line interface, do a scan, but it's asking DynamoDB, hey, as you're doing this, tell me what the stats are of the request. How many items were read, how many were returned to me, and how many read units I'm going to be billed against. In this case, we're also going to hide the actual records. We're most interested in the stats, right? This is an efficiency demo. So the first one we can do is scan, the simplest way to start. And we can see here there's 17 items in the table, and all 17 were returned to me. 34.5 RCUs were consumed. Remember that 50% discount, so that's about 70 times 4, 280 kilobytes represented in the return from the whole table. Now let's say we want to only get items that are in cart 1, item collection 1. So we can do a filter for cart 1. The problem with the filter is that we're still scanning all the items, even if we're knocking out most of them before they get back to us. So we get the exact same charge. So filter is not quite as efficient. We can do get.sh or get item. And the simplest way is just a key value lookup, provide a key and get a value. And you can see some of the attributes there. You can hit space and Q and get out of the paging program. And then we see that it consumed 2.5 RCUs for the 20 kilobyte item. Another nice thing we can do is to specify, hey, I don't really want to see all those attributes. Maybe I just want to see price. So limit the attributes that are projected back at me. Which is nice, less data comes back, but however, the bill is still the same. We still are charged as if we read the entire item, so keep that in mind. And then finally, we can ask for strong consistency with our API calls. If we're in a certain situation where we need to make sure that there's no possibility of read after write having a stale copy of the data, we can just you can do that, and we'll see that the consumed read capacity has doubled up to 5.0. Okay, the next one I want to show is batch get. And
the take home there, that one is to use those default eventual consistent reads everywhere we can. And we offer the strong consistency, which is really great. Use it when you really need strong consistency, when it's truly justified.
Mm-hmm. Here's a really powerful one, batch get. It sounds fairly simple, right? In this case, what I'm going to do is say, hey, I want to look at John Styles' shopping cart. I want to get 2 items back. Number one, one of the products in his cart, and also a full product description of that. So in a traditional database, this might be a join against the cart and a product table with a foreign key join. But here, we're just going to say, hey, get me these 2 things. There's the first item. There's the product cart information with a price and a quantity. Right, and then the second item is product 300's full details. Totally different type of item. It's living in the table there. But essentially, because they both have a product, they both can be queried with a batch get, we can get them back together. In a normal SQL operation, right, wouldn't you, SQL result sets can be too normalized. Imagine getting this huge amount of text back twice because it appears 2 times on the result set. So with DynamoDB, we get, in this case, we get back exactly what we need, and we can use all the data that we got back in our application. Great, so the next one we're going to do is a query. And query is all of our favorites. It starts off by just looking at an item collection identified by a partition key. Query all the items in cart 1. So rather than the scan and filter we saw earlier, now we're only scanning 4 items because Dynamo was able to go and locate that collection and get them all back, and 10 RCUs are consumed there. Just like scan, query has a filter operation. So we could do, hey, look at this this item collection. and find the item in the cart where the filter expression matches orange. And we see we're not as efficient, right? We still have to scan all 4 items, but we only got back one back that matched the filter conditions, and we're still getting the same charge as if we had returned the entire collection. So we can do a little bit better, I think. We can do query sort key, and here's where the power of sort key expressions comes in. That orange corresponds to the sort key attribute, which is product 400. And now when we run that, we get back one item. Returned and scanned are both one item, and the consumed RCUs is way down as well, because we're very efficiently locating that item, almost, in this case, like a get item would have done. Okay, so let's delete some items. Let's delete that same item. Now you might think a delete is totally free, just like dropping an item in the trash can. But it's really a type of write, isn't it? And as such, we're charged with the the higher of the original size and the final size of the item. In this case, the 20 kilobytes. So this is maybe a way for us to think about TTL, time to live, automatic free deletion that's possible with the right type of timestamp in our table. We can do puts. So here's a put, and there's a data file, a JSON file that is going to be loaded. It's going to load in a new item for cart 7, product 700. It's a 20 kilobyte item. No real surprises there. We're charged according to how much data we put in. Now let's update that. Let's say we want to update cart 7, product 700, and change the price to something else. What do you think the charge will be, Pete? Price is a pretty small attribute to be changing, right? Shouldn't be too bad.
I have a feeling, we need to essentially upsort or replace the entire item, though.
That's true, yeah. And look at that. Even though I only updated the price, I'd still get charged to 20 write units of capacity. So it's essentially replacing the entire item itself. All right. Well, you know what? I think the problem really is that customer description attribute is just too darn big. Let's knock that down a bit.
I like that idea.
Let's make it something, how about much smaller? More 20.
Much less too. Much easier to read.
Yes, exactly. Yeah. More lorem ipsums. But you know what? It's still giving me that 20 write unit bill. And that's, of course, because the original item was large. So we're still overwriting that, as it were, and getting a bill of 20 WCUs. But the good news is now that we've changed that, if we change the price now, the whole item is now small, and so any further changes to it will get a much smaller charge of 1 capacity unit.
Great.
All right, so that's a nice whirlwind summary of the core operations. I think right now we'll go ahead and add a GSI. And the GSI is added. So that's essentially a new view of our data. Let's take a look at what this looks like. So instead of sorting by product, by PK and SK, we're going to sort by an alternate means of product name and price. And you can see the different grouping here. Now it's very clear that products are grouped together, and they're sorted alphabetically by their price. So we should be able to do queries and nice, powerful operations using that price, for example. So let's do an update. Let's change the price of product 100 and see what happens. Okay, so now the return consumed capacity is showing us a little bit more. It's showing us a breakdown of 60 capacity units needed, Pete. Wow. 20 on the base table, but 40 on the GSI. It's a little bit strange, right? What's happening here is...
Yeah, we're updating the record in the base table in the primary index, and we're changing an attribute that's not part of the primary key for that index, but it is part of the primary key in that global secondary index. So basically what happens when we're propagating that change into the global secondary index is we have to get rid of the original view of that item. It has a new primary key. We have to delete the original view in the index, and we have to replace it by writing a replacement that has the updated primary key. So this is something to understand in terms of the rights consumed in maintaining a global secondary index. These changes can essentially, maintaining a global secondary index can consume anywhere from 0 to 2 times what we're consuming in the base table. Based on whether it's and what we're projecting and how we're doing our updates.
Let's just change the price then, and that might be a bit simpler. So changing the price alone, the price was not part of the GSI's keys, was it? The price is still reflected in the global secondary index, so we do see, oh, I'm sorry, let's change the quantity. We already did that one. The quantity now is not represented. Let's change the quantity to 5.
Edit that part out in the recording.
Sounds good. All right, so what we have here, we have a little bit less of a bill. We have 40 capacity units needed. The quantity is not part of the key of this GSI, so it's still a change to the GSI, an overwrite, if you will, to the same item. So we are billed once for the base table and once for the GSI.
Yeah.
All right, let's do our final update. Not all these items actually made it into the GSI. Right, not all the items have a price. This is a somewhat sparse GSI. So if we were to update an item, a customer master item, like we see here, and just change John Stiles' address, because it's not part of the GSI, it's really just a base table operation, and it was a small record to begin with. So it's a small results coming out in terms of the right bill. All right, so that's moving on. That's pretty much it for the demos, but I should mention that all these scans and queries that you saw here can be run against the base table and the GSI in exactly the same way. GSIs have their own partition key and usually a sort key. So you can just point to the GSI and run those. The final thing, Pete, I get a question from a customer. How would I do a get item from a GSI, and how would I actually write and update a GSI directly? Can you explain that?
Your customer brought you a trick question. Here's the thing. We can't update the GSI directly. We can't write into a secondary index. We always write into the primary index, and we let DynamoDB propagate those changes to the secondary indexes. And in the topic of why can't you get item to a GSI, the difference there is that in our primary index, the partition key and optional sort key, that primary key, is used as a unique identifier. So we know that there is only one item in our primary index that has the partition key and sort key for that item. In the global secondary index, we're organizing things differently. So actually, we might, for the same partition key value and sort key value, the same primary key in our global secondary index or local secondary index, we might actually have multiple records. And so get item doesn't really make sense, even though we can supply a partition key and a sort key to that secondary index. We might get multiple results back from that. It's not really getting an item, it's more of a query. And so in our secondary indexes, the read APIs that are supported are scan or query. We can't use a get item or a batch get item. All right, back to the slides. So, what can we do to help make some of this filtering more efficient? We talked about the situation where we were going to use a filter expression to narrow things down based on the status in our example that we looked at a moment ago, and then we're going to get them back in sorted order using that sort key. And unfortunately, that means that depending on the mix of different status values in that item collection, we might be consuming a lot more reads than we really use, or that we would cover the results that we truly want after the filtering. So one thing we can do, and a really common thing in DynamoDB advanced models, is to use these concatenated sort key values and to build sort of a hierarchy from left to right. If we took our status attribute and then we looked at our date attribute, and then we combined those to make a single attribute value, a string where we've used the status And then we have a separator, maybe a hash character would work here, and then our date. Now we can actually build indexes around this that allow us to do everything we needed to do using the sort key condition instead of relying on the filter expression. So for example, we would have Sue here that has 3 different items in carts. Some are active, one is saved. And if we want to get Sue's active cart items, we can say, use a query to say, for the Sue item collection, please give me back all of the items in the collection that begin with active hash. And those will be returned to us still in sorted order by timestamp. So this gives us a lot of power to build these hierarchies and be more selective within our sort key condition instead of relying so much on the filter expression. There is our combined status date attribute, and here's where we can make a begins with on that status. Only get those 2 records back and only consume the reads associated with those. So can we extend on that,
All right.
Rob?
I think so. Yeah, that begins with has got my mind thinking of some ideas here. I think we can build a hierarchy, a full hierarchy as deep as we like, just by virtue of how we write these sort keys. A common pattern we see is to have delimiters like a pound key, for example, that will separate different parts of a hierarchy, like an address hierarchy, for example, or even a date of year, month, and day. All right, and so by writing carefully, you can see that you could easily do a begins with state of NY, begins with state of Washington, and also begins with SEA up to left to right, and stop there. And it essentially would use the sort key expression to get back efficiently only the items that match that condition.
Yeah, that is actually a really powerful pattern for hierarchical relationships between different levels of item. Here we could be very selective about looks like choosing some of the Amazon buildings in different locations.
Mm-hmm.
Great. So here's the thing: we have our shopping cart and we built it this way. Now we have this new pattern. Everything was going great, and then maybe the marketing department comes along and says, we have this idea. What we want to do is run a special price on maybe the Echo Dot, right? And we want you to be able to tell us, can you give me the list of customers' carts that are active and which have this particular Echo Dot device added in the cart? So these customers have added it to the cart and not committed to actually submitting the order yet. And the reason they want to find those people is they want to reach out to them or notify them that we're running this special price. It's going to be discounted through this particular time and date. And they want to let those folks know, maybe encourage them to submit their order while they can take advantage of the better price. How could we do that? I mean, this is a new pattern, right? How can we support new access patterns?
Right. I think we can use the GSI. We can use the partition key as an alternate item collection, right? And use the item skew to locate the item in question, the Echo Dot, right? And then use a sort key. Maybe begins with the status we're looking for. Maybe even further filter by date, that most recent items, for example.
Yeah, exactly. We're basically building we're collecting the same information in different ways. We can add these GSIs. They're online indexes. So if a new particular pattern comes up that we want to be able to support, we can add those to our DynamoDB table, and the service will build those on the back end for us and let us know when they're ready for queries. So pretty great option to have.
Very good.
Another option here is, if we have kind of a needle in a haystack pattern, and this really builds on the concept of flexible schema. Not every item in our table has to have the same set of attributes, and in fact, maybe we can kind of tag a few of them or selectively mark a few of them for some other process that we have by adding an additional attribute. Here we see that we could, for the items that are added into the cart, we let people indicate whether the item is a gift and who it's for. So we can use this then, if our GSI is defined to use that attribute, only the items that have that attribute are going to be propagated into the index. And so here's a case where actually a scan is a very, very efficient approach. We're only going to have items in this GSI that have the gift marker. And so when we scan that GSI, we're going to get exactly the result sets that we want very, very efficiently.
Pretty cool. Here's a look at version control. We talked already about optimistic locking, so this is taking that a bit further, right? And we use this often within Amazon. The idea of keeping a version number. So you see that version, the first item there, the version 0 root. That's essentially always the current version of an item that we're working on and changing. We track the current version there is 2, right? And then if we wanted to work on it, we might copy that version 0 to a new 2+1 version 3 and store it there. Do our updates, maybe change some attributes, work on it. Once we're happy with that, then we can copy it back to the original 0 item and overwrite the version number and set it to a new version number, but also do the whole thing conditionally if nobody else has beat us to the punch and made the same kind of change.
Yeah, this is a great pattern and takes advantage of that optimistic locking. Very, very powerful again. Great. So one of the things we often talk about when we're talking about scaling with DynamoDB is taking advantage of that hashing of the partition key. That's what we use to assign any particular item to a particular partition on the back end of our storage. And one of the issues we can have there is that distribution is rarely perfect. Sometimes it's very much skewed to a particular set of items or a part of that hash range. So what are some of the things that we can do to work around those situations and to do that efficiently?
Here we see an example of a report processing app that we're going to go through. And the idea here is that we have users and they have reports. And the reports, a lot of the report data is actually included right in the Dynamo item. So each item will have 256 kilobytes of payload of extra data, if you will. So they're pretty large items. The maximum size is 400 kilobytes for an item. We also are constantly updating the status of these items. So it could be pending today, it could be processed, it could be some other status. So as we saw in the demo, as we do writes to these items, 256 kilobyte item could be a quite expensive thing to be updating frequently. So we have a problem. Maybe our manager is complaining the bill is too high for DynamoDB. So let's see how we might approach an alternate design.
Great. Yeah. So one of the things that I see here that kind of troubles me in this initial idea to begin with is that actually, you know, I've got to think that a document needs to be uniquely identified. And if we look at the primary key of how we're storing these, we're using a partition key value which is an owner, a report owner, and then a status date for the sort key. So the combination of these, a partition key as a primary key, doesn't necessarily guarantee that the document ID is unique. Probably we want to use some kind of an alternate approach where we have a unique identifier for the documents. Here is that example of actually calculating out how many read units would be consumed to read those 50 very large items. And unfortunately, you know, we're really not making use of this. This is essentially like maybe an online email application where we're really just looking for the list, a summarized list of items or messages that we want to be able to dig into more deeply as we wish. So let's take a different approach here. You know, if we use this unique report ID as our primary key, that's going to make sure that we cannot possibly have a document that has the same report ID, which is great. That's giving us a uniqueness guarantee. We're going to move the owner ID into its separate attribute here. We don't need a sort key in this particular iteration of our design. We'll also add a summary. So maybe this is almost like the email client that you might want to have a brief blurb, maybe the first paragraph of the message, not the entire message with all its attachments, or maybe the subject line. And then we still have our status date because we're going to need that for some of our query patterns. We'll then build a GSI on this, and it's going to selectively project from that GSI. we're not going to project all of the attributes, but we will create a primary key, which is made up of the owner ID as the partition key, and then the status date as the sort key. We'll include the report ID, which is unique, and we'll include the summary. But we're not going to project the bulk data, this document data, which is a big 256 kilobyte blob of document information. And in doing this, we can now actually make our query to find, for Paula when she logs in the morning and wants to see the list of, up to 50 reports that belong to her and are in pending status, and get them back in date sorted order. She can now do this, and that query will probably come in under a single read unit. So much more powerful, and then based on that, she could click on one of those report IDs to go to the detailed view of that report when she wants to work on it. So that optimizes the read side of things. Is there anything we can do to optimize the writes? Because one of the things that I'm thinking about in this design here is that we might be updating that status date very frequently. The lifetime of a report that's added, we may make some occasional updates to those reports, but I bet we're going to update the status date many times over the lifetime of that report ID. What can we do about that, Rob?
Yeah, that's a real challenge for sure. Well, keep in mind the base table was initially partitioned, or it's a partition key of the report ID with no real sort key. I think we should add a sort key, Pete. I think if we add a sort key that's got the two different types of items, like a metadata, a small version of the report, and then the full report in its own item with the blob. Right, and that way the metadata itself could have the status that's updated frequently as a small item with much less write consumption.
I like it. Yeah, so we take what was an item and we break it out into a collection of two unique items. We still have our uniqueness guarantee because we know there can be only one report named AFED and with a sort key value that's AFED meta. But we're keeping the smaller frequently updated attributes in that metadata item. So when we want to update one of those things, it's going to be a single write unit instead of the entire 256. This just gives us more flexibility, and the nice thing about breaking this into a collection of two items is that when we want to, we can still go and read that item collection, get the metadata and the report itself, and the query is going to aggregate those sizes and round up for the read. So it saves us on the write consumption, and it doesn't cost us anything more on the read side of things.
Pretty awesome.
A much better optimized design, and then we can look at our GSI, which becomes a sparse GSI, because we're going to use the primary key for that GSI will be owner ID as partition key, and the status date as a sort key, and it still has the summary and the report ID that's here. The only records from the base table that are going to be propagated into this GSI are the metadata items. So we get the ability to meet our query, we minimize our write consumption, and we're minimizing our read consumption. So this I feel a lot more confident about as a well-optimized design for our query patterns that we need to support for our application. All right, Rob, you're up again. More demos.
All right, let's do this. Just share my screen. Okay, for this demo, we're going to do a slightly different thing. We're going to use the NoSQL Workbench. Much more on this time next week. Pretty powerful, the modeling tool. But for now, you'll see in the GitHub samples, there's a reports folder. And I'm going to go ahead and import the report management JSON model. Bring it into the Workbench here. And we can certainly take a look at the data, but let's first just push this into AWS. I'll put it into US East 1. And then we'll have a chance to do some actual live scans against it. And then we can do exactly the types of updates you were talking about, updating the status of one of these reports, and we'll see exactly how much consumption we have. Hopefully nothing too shocking.
This is excellent. It's almost like, Rob, you knew I was going to propose this design.
Exactly. So there we see report 92B. We see it split in half with a metadata flavor and then the full report. All right, so let's go ahead and run this script, status update. And we're going to change essentially the sort key date here in the GSI from 10:04 to 10:05. Okay, it did sort of amplify our writes because it's changing its position within that GSI. But remember, the whole item itself was pretty tiny, so we're getting charged their 3 capacity units.
Much better than 256.
Much better. And then here's the best part. We can go ahead and query the GSI for a certain owner like Paula, and do have it do the begins with. Query that GSI. This should give us a preview of all the items without actually reading the full payload of bulk of the items. So there we see it. There's a preview of her 2 reports that are there. All right, so that's that demo.
All right, excellent. Let's go back to the slide deck. We need to pick up the pace here, I think. Have a lot more stuff to cover, and I don't want to cut us short.
Mm-hmm.
Okay, so again, let's talk about some of the situations we might have to face where we have concentrated throughput. First, let's look at maybe a read scenario. This might be, again, we're going to use kind of an Amazon theme example here. It might be a product catalog table, and it's Prime Day, and we're running maybe a deal on the Instant Pot. So that Instant Pot is going to be a very, very popular item in the catalog table. We might have shoppers trying to read that item 50,000 times per second. And a DynamoDB item can support up to 3,000 read units. So that's not going to work very well. The first thing I will point out is that if we're making an eventually consistent read of the Instant Pot record, which is almost certainly a very reasonable thing to do, we can actually get 6,000 reads per second for that record. So that's the first thing to note about scaling this and covering the requirements. What else can we do? The first thing we could consider is maybe some caching. If we made use of a cache either in the on the client itself, or maybe using an external cache, a centralized cache like DAX, Dynamo Accelerator, or it could be Elastic Cache. Whatever we want to use for our caching scenario, what it's going to do is even out that distribution of traffic across our items in our table. It's going to vastly reduce the number of reads overall, and that's going to be excellent. It's going to probably save us some significant money. And it will also reduce the latency of that read, which is a great thing. So we're going to even out the distribution of traffic. It's going to reduce that overall consumption, but I want to point out a really excellent article on the new AWS Builders Library. It talks about the potential for cache addiction. So be careful about the availability impact here. When we place something between our client and our data store, we can actually reduce reliability because there's more components. Maybe we want our client to fall back to reading directly from DynamoDB if the cache is unavailable for some reason. What happens when we hit that same Instapot record with 50,000 reads per second if the cache is not working for us? It's not going to go well, right? We're going to see some throttling. That's a bad customer experience. And if we're being customer obsessed, what else can we do? What we can do is we can actually distribute that same traffic across more items. Consider putting the same Instapot catalog information in 10 items, Instapot 0 through Instapot 9. The client chooses one of those items randomly for the reads. And now we can support actually up to 60,000 reads per second. Now we could potentially use this to roll out changes to such high traffic catalog items progressively, almost like a rolling deployment. But what if we want to update a few or all of the items? We could use maybe batch write items, or maybe we really want to make sure that all of those copies of the Instapot catalog item are updated at the same time, atomically, all or nothing. Is this bringing anything to mind for you, Rob?
Transact write items, I think would do it.
Yeah, good call. I like it. Making me think of that too. So some really interesting possibilities there. How about what can we do for write throughput concentrations?
Well, I think we can take a similar approach, right? In the case of the Instant Pot or writing, or in an election as we see here, let's say we have a massive amount of write traffic, more than the 1,000 per second writes that we can nominally support. Right, so we can sort of shard with an artificial sharding key. We could say, hey, write to candidate A, modulo the, some random number between 0 and 5, right? And we'll still have to gather those and assemble those later when we do our final tallies, but essentially we'll be able to fan out the writes to multiple partition keys within Dynamo.
Excellent. Yeah, so we're going to scatter these across. We might even not know. We might have 10 different candidates, and we're not sure which one will be the one that runs hot. So we might use this same pattern and have 5 different items to accommodate their counts. We just, again, each count gets a random choice of one of those items, and we're essentially scattering to distribute that write traffic. We wind up with these candidate A1 through A4 and an individual vote counter. We'll put this maybe in a table for count shards. So what about when we want to find out exactly what is the total, what is the running count for this candidate? We're going to need something to do the gather on the other side of this scatter-gather type of a program. And that might be a Lambda function, and we might run it live, or we might do it kind of periodically. It's a scheduled process that goes out and collects those items for us, builds a summary, so sums the individual vote counts across each of these shards, and gives us a total. We might want to do that once a second, because let's face it, maybe we have a dashboard that we want people to be able to see relative standings, and a 1 second increment on that is probably fine for that, rather than going and reading this every time. The most efficient way to go and gather all of these different individual pieces in order to do the summary would be a scan. We can scan that table. If the only thing that's in that table is some of these sharded vote counters, we scan it, we get everything we need to build our summaries, and we could store this in a separate a dashboard table or somewhere that's easy for our other applications to go gather the information for display.
A second table.
Right, so what was that?
A second table you mentioned. Wow. Okay. Yeah, possible.
So how about let's talk about a little bit about external indexes. Some of the things that we can do to manage item life cycles and some asynchronous workflows. Of course, that's going to depend on DynamoDB streams. Why don't you tell us a little bit about those?
Yeah, sure. DynamoDB streams is really the change log coming off the database. So any and all changes that happen, you're able to access those through the stream. And there's a lot of automation. Typically, these are tied to an event trigger that fires off an AWS Lambda function, which runs your custom code. So with that, we can do all kinds of things. The Lambda function can call any one of the 175 AWS services, or it can just loop back and point to your original table and maybe write some kind of aggregation, like maybe a counter that it's incrementing, or something we want to track in the base table as part of our application. Typically, it also might call out to the Elasticsearch service, which is a full-blown search engine, or it could be pointed towards Kinesis Data Firehose, and that could be the beginning of a pipeline where data moves into S3 and then is queryable through the Amazon Athena through Parquet files. So with Athena, of course, you can do more like ad hoc queries, more SQL-type questions against your data.
This is awesome. I can see combining this with TTL to kind of expire our cold data and still be able to make occasional ad hoc queries across it using Athena, and all serverless. I do like that. So one last thing we could do is just have that Lambda function looking for particular types of changes or particular types of changes to certain records, and we might take some action on that. We might place something in a queue for further processing, or just send a notification through SNS. So there's any number of different possibilities here, and this one is nice because I think it's kind of an example of that polyglot persistence, where it's the same data, but we want to index it different ways, and so we're going to use multiple AWS services to get the best we possibly can from each of those indexing requirements. All right, now we promised when we set up this session that we would give some broad strategy on how to approach building designs with DynamoDB. And one of the first questions we get from many people is, how many tables? Because we hear about this single design table design concept, and then when we start to do our design, we wind up with more than one table, and we're upset about it. We can see that Plato here actually recommends one table. Aristotle wants 5. So Rob, what is the strategy we should bring to this?
Pete, there really is no hard and fast rule. I think the reason why we focus on a single table design is to really change our thinking. Most of us started off as relational developers, and we love to have 20 or 50 tables for all the different entities. So we try to denormalize, we try to get things into a much smaller number of tables, and sometimes one table will work just fine. Oftentimes we see a table per microservice, for example. But it doesn't always have to be that way. There are some certain advantages to having multiple tables. For example, if you have different tables, you can have a more descriptive name of the table and more descriptive attribute names instead of trying to overload different types of items into the same table. You also might have streams enabled on one table but not another table, right? Because streams operate on the entire table and look at every change.
Sure. So another one is scan. You know, maybe you have certain sets of items you want to be able to run a daily scan on for some ETL that you're going to use. It's just a business requirement, and you don't want to necessarily have to scan all of your items, just that certain set of items. So for me, I think, you know, you don't want to have more tables than you need, because now you have to operate more things and deploy more things, and that just makes operations more complex. But you need the right number of tables to get your job done optimally, make it reliable, and the way that I think about the single table design, or whether 2 items or 2 item collections belong in the same table or not, is, you know, I come back to those item collections, and I think if these items I'm going to look up literally as separate, denormalized reference pieces of information, I'm never going to build an item collection around these 2 different items, then there's really not a big downside to having them in separate tables. So I fall back then to some of these requirements around being able to do scans or streams, and I use that to guide me. So, you know, the number of tables required to match these priorities is often more than 1. That's okay, but please try to denormalize when you can, and let the DynamoDB item collections and indexes do the work for you. If you start with a traditional relational mindset and third normal form, many different tables, a table for each entity type, you know, you're probably going to miss some really awesome opportunities to benefit from these unique strengths of DynamoDB. All right, so Rob, here we go. This is Rob's secret to data modeling success.
Right, how to model your data with DynamoDB. Well, I think the first thing is to, you know, constantly study and learn more about Dynamo. As we learn more, I think ideas come to us. Some high-level steps, as you see here. First is think of the entities. You know, entities don't go away depending on which database you use. So we always have this idea of logical groupings of customers or products or things like that. And the entities themselves have attributes, and they also have relationships with each other. So we need to maintain that kind of thinking. Next step would be probably to document and list all your access patterns, put them into a spreadsheet, and socialize it. You know, get buy-in, make sure we're all on the same page with what our application is designed to do. Very often we see the access patterns tie one-to-one to the actual data access functions that we're building within our application. Right, and every function has a set of input parameters and a set of return data that comes back. So list those out, and it'll help us to build those functions. Also, make the list finite. You know, we want to limit our scope for sure for all projects, but it's especially important for DynamoDB. We want to really focus on something that is well understood and has you know, repeatability. Something like processing a shopping cart. Dynamo is not so good for open-ended you know, questioning and you know, SQL queries where we don't even know what access patterns will be. Next probably would be define your uniqueness. Define primary keys for items. Pay special attention to any items that have to be strongly consistent on reads. So if there's any need for that, those types of lookups will have to be against the base table and against the primary key of the base table, so you can do a strong read. But apart from that, we can overload tables. We can have different types of items in the same table, and we can also have collections, as Pete talked about and illustrated. Finally, you know, think about layering on GSIs. So global secondary indexes will, you know, regroup your data, of course. Make sure you have all the attributes laid out. Sometimes it makes sense to space out and even duplicate certain attributes here and there. Maybe we're going to duplicate an attribute, but only on half the items because we want a more sparse index to locate those and pick those up. But think about which GSIs will answer different questions from your business. And then finally, build it. Try it out. Build it in the workbench. Deploy it. See how it works. Try your access patterns. Make sure they work. Look at the return consume capacity so we know, how expensive different types of reads and writes are. And rinse and repeat. Those are the 5 steps.
Yeah, I totally agree with that. I think that's a really a fast track to getting to a point where you're close to an optimal design. You're really setting yourself up for success if you follow this kind of pattern. And I think that's really very close to all we have for today. We may have time for a couple of questions. I want to thank everybody for joining us today, and I want to suggest that catch up with us again, or with Sean Shriver and Rick Houlihan next week. They're going to use many of these things that we talked about to show you how to make really good use of the NoSQL Workbench for DynamoDB, how you can use that tool to iterate on designs and really formulate exactly what you need. There is the link right there for some of these demos that we did. There's a number of other demos. I'd encourage you to take a look, have a look at what we're actually doing in those operations and understand that return consumed capacity. We have some other really great free labs on Amazon DynamoDBLabs.com, and please do follow us on Twitter with the DynamoDB handle for updates. I do want to say I had one question that someone had pointed out, since we just have a couple of minutes here, which was a good one, I think. It was talking about the alternative, rather than just writing an item in the base table and having it projected or propagated into a global secondary index. How is that different, and why would you choose to do that as opposed to just writing 2 items into tables, maybe same table or different tables, essentially building 2 ways to index the same piece of information? And really the answer there is that the GSI is going to take care of that for you. If you if you took that on your own, you kind of have some more complexity there. What if one part of, or one of the items writes successfully and then the other doesn't? It gets a little bit difficult for, sorry, let me get rid of that. Gets a little bit difficult to manage those 2 items. If you did truly have the requirement to index the same data under 2 different item collections, and you needed strong consistency on both of those, one approach might be to do those 2 item writes, maintain them separately, and think about wrapping those in a transactional write, because now you can say they're either both going to succeed or both fail. It's a much simpler, easier, and cleaner way for you to manage that from the application perspective. So that's another really, I think, powerful option for managing additional indexing using those transactions. All right, so I had a reminder here to please fill in the form over here. If you would like to, I think we might have missed that opportunity, but please, if you do want some additional help from some of the DynamoDB experts on the AWS side of things, feel free to reach out. As I said, follow us on Twitter. We can definitely keep in contact that way. Thank you very much, Alex Debris, for joining today, and all of the rest of the folks that helped us to answer all the questions.
Thank you, everyone. It's been a pleasure. Yeah. See you next time.
A little bit of time here to give some feedback, but thanks very much for joining in, and hopefully we'll see many of you again next week.
Thank you. Take care, everyone.